So, students, good morning. As we said last lesson, that today we shall really test the common base and common collector amplifiers and also a multi-stage amplifier. Now, common emitter amplifier simulation test we have already done. Look at this common base configuration and make sure to yourself that the configuration matches with the theoretical study that we have done in our last lesson. This is a BJT, the same R1, R2, this R2 bypass capacitor, so that this current straight right here. And this is a voltage supply 10 volt given to the collector through the RC. This is a coupling capacitor and this is the out. Theoretical characteristics of this amplifier we have already discussed. So today we shall only test just to show you that such an amplifier really exists. It's not all theoretical. So let us switch on the oscilloscope. This is the oscilloscope and let's run. This is a supply, signal supply. I have made it 707 millivolt RMS, which makes 2 volt peak to peak. And that makes it easy to measure and calculate. So let's run this oscillator. So I'll reverse the screen so that it is all visible to you. Okay. So this is oscillogram. Let's spread it a little bit. Right. Now, this blue line is the input. And this red line is the output. But of course, the scales are different. If you can see here, if I make both the scales same, then this is also 2 volt per division. This is also 2 volt per division. If I make both the scales same, and you can see there is some gain in this amplifier. This is 2 volt. This is the red line is the output and blue line is the input. So there is a common base amplifier possible. So what we shall measure now is the gain, right? For that, we connect a voltmeter here and we connect another voltmeter here and run it once again. We close this oscillogram and we run it once again till values appear right. Now these figures may be a little too small for you to have a look, so I zoom in. I think you can see now. Output voltage peak to peak is 8.32 volt and input voltage peak to peak is 2 volt. So what is the gain? 8.32 by 2. I have a calculator with me. You can also calculate. It is 8.32 by 2. It is equal to 0.32 divided by 2. That is equal to 4.16. So voltage gain here is 4, and I write it here 16. The voltage gain. I have written it. What is the current gain? I have to remove the voltmeters and I have to put the current probes here and another current probe here and run it once again. Becomes more or less stable. See, current peak to peak at the output is 832 microampere. It's 9.38 milliampere. So current gain is less than 1. 832 microampere means 0.832 milliampere. So it is 0.832 divided by input is 9.38 9.38 milliampere, 9.38 milliampere. So current gain is 0.09. 0.09, I have already mentioned it here because I measured it already. So what do you find? Current gain is very small. But mind it, in common emitter amplifier, current gain is equal to HFE of the beta, around HFE of the beta. Here it is very, very small, and voltage gain is also very, very small. These are the properties of, or these are the difference of properties of current gain and voltage gain. Difference of properties of various gains and other parameters between common base mode of amplifier and common emitter mode of amplifier. If you trying it, because this simulation you can do at your home, you don't have to do at your college. You will gather enough insight into functioning of these various amplifiers, right? Now let us measure the input resistance and output resistance. This is the input voltage. So once again, we connect a voltmeter here and we connect a ammeter here so that we can see the current voltage ratio, right? So it is running. Hope you can see, or else I'll zoom in further. Yeah, or this is not getting zoomed in. That remains same. Here current is 9.38 milliampere and voltage is 2 volt. So resistance is 2 volt divided by 9.38 milli, right? 2 volt means 2000 millivolt divided by 9.38 milli is equal to 213 ohm. 213 ohm. So I have written 208 me in my last measurement. So let me make it 213, 213 ohm, right? Now we shall measure the output resistance. Measuring output resistance is something different. Measure the output resistance. This voltage source has to be open circuited, right? And this load also has to be open circuited because the load is not a part of your system. And then you have to really, if you are, there are impedance meters normally used in very good laboratories. But in normally, maybe in your institute, you may not have an impedance meter, you have multimeters. Multimeters will not measure impedance because if you apply a multimeter here, let's say, the output, what will happen? Multimeters measure resistance. Multimeter injects a DC current into the system, and multimeter within itself measures the voltage and current and shows you the resistance value. Multimeters do not, but DC if you supply, it will not work because there are so many decoupling, coupling capacitors. So you have to give a AC voltage and measure the AC voltage and current. So what I do, I copy this AC voltage source here temporarily for you, and I give a AC supply to the system from the backward side. That means from the output side, right? Then I measure this AC voltage and this AC current and this AC current. And if I run it now, I'll find out what is the voltage and current if I supply from the reverse side. I find current is 85.5 microampere and voltage peak to peak is 2 volt. So it will be 2 divided by 85 point micro. So it is 2, I make 2000, that is millivolt. And this micro can be expressed in a 0.0855. 0.0855. That makes 23.4 kilo, something like 23.4 kilo. So output impedance is 0.4 kilo ohm. This is the value when the load is disconnected. Now, if you connect this load, 10K load, then what is the value? It is 2 volt by 581 microampere, right? So 1000 divided by 0.581, 0.581 is equal to 3.4 kilo. Now, if this power supply is kept connected and this AC signal is supposed to short circuit the power supply, then what is the value? It is 2 volt peak to peak divided by 7.34 milliampere. So it is 2000 divided by 7.34. It is 272 ohm. So output impedance is 272 ohm. This is 272 ohm, right? So we have got these values. This I removed because this was not a part of the amplifier. And then we have to also see the frequency characteristics. The system was running, frequency characteristics should be available here. See, this is the frequency characteristics. I increase the level a little bit so you can see it correctly. I reverse the screen. Now you can see the frequency characteristics correctly. Now let's go to the mid frequency where the gain is flat. Find that the gain is 12.79 dB. Lower cutoff frequency is defined as 3 dB less. So 12.79 minus 3, it will be 9.79 or 9.8. So let us go here. Let us see where it is 9.8. It is this value 9.8. 9.8. Look at this value. I want trying to make it 9.8. 9.99, 9.5, or this is 9.99. It will be something in between this. 9.99 is 10 hertz and 9.7 is 10 hertz. So you can say the lower cutoff frequency is 10 hertz for this particular amplifier. So this lower cutoff frequency we can say is 10 hertz. And this upper cutoff frequency again, we have to measure it. This was 12.8. I have to go to 9.8, 9.8, 9.77, 9.1, and this is 8.77. So this is 9.4. Let me try manually. 9.8 I want to make. 9.1, 9.4, 9.7. Let us keep it here. This frequency is 65.6 megahertz. Say 66 megahertz. So F2 is 66 megahertz. So what we have done, we have completed the testing and measurement of a common base amplifier. That should give you an insight. That should satisfy you. Yes, such an amplifier exists, right? Let's go to common collector amplifier or common which is called emitter follower amplifier. That also we have discussed in our theoretical class. This is the emitter follower amplifier, right? Amplifier which I have already made. I during my design I had to collect. I connected these emitters and voltmeters to check that biasing is okay. So don't bother, don't get worried about this. These are the emitters and voltmeters. You also will connect initially to check that biasing is okay. So ignore them. Here you see this is the BJT and this is the emitter resistor 1.2K, and output is taken from this emitter resistor through this coupling capacitor and the 10K load. And input side, the similar, there are biasing, R1, R2, etc. And another point that you have noted in your theoretical class, the collector is directly connected to the power supply. There is no collector resistance. There is an input source and there is an input coupling capacitor. And you remember what we discussed during this common emitter follower? That its voltage gain is almost equal to 1. It does not provide much of a voltage gain, right? So this is the oscilloscope. Let's turn on the oscilloscope, reverse the screen. That will make easy to, let's turn on the oscilloscope. And I reverse the screen. You see the blue line and red line are more or less same. That means there is no gain. If I make it larger in the Y scale, still I cannot show you. Actually, the output red line is supposed to be a little 1% small than, but in the small screen, 1% or 2% is not visible, right? So here the gain is almost equal to 1. Another voltmeter here at the source. Here, output is 83.2 millivolt, input is 84.8 millivolt. So output is little less than the input. So actual gain is 83.2 divided by 84.8, 84.8. This is equal to 0.98. So this gain is 0.98, right? We can see the current gain, remove voltmeters, put in current meters, put in a current meter on the load, or you can put the current meter here also. Output current is 8.32 microampere and input current is 7.88. So current gain is 8.32 divided by 7.88. 7.88 is 1.05. So current gain is 1.05. 1.05. Now we can measure the input resistance, output resistance. I connect a voltmeter here. See what is the input voltage and what is the input current. Input voltage is, peak to peak input voltage is 84.8 millivolt and current is 7.88 microampere, right? So input resistance is 84.8 millivolt. 84, 84.8 millivolt means 84800, 84800 micro divided by current is 7.88. 7.88 micro. So input resistance becomes 10.76 kilo ohm. 10.76 kilo. If, if you have already noted the input resistance of common base or common emitter mode, their input resistances were smaller. We discussed in our theoretical classes that input resistance or input impedance of a common emitter mode is very high. Similarly, you can measure the output resistance also. But I will show you another method by using a software impedance meter. That will be useful to you when you use it in your lab or at your home. This is the impedance meter. The positive end you connect to here and negative end you connect to the common, right? And you switch on and measurement you do at 1 kilohertz, 1000 start frequency, and end frequency is also 1000, right? Run it. It will give you, see, this is the resistance, this is the reactance, and this is the impedance. It is 305.9. Say, let us say 306 ohm, right? So output impedance is 306 ohm. 306 ohm. If you have already noted, other two versions will not have so low output impedance or so high input impedance. That is the purpose of this common emitter, common collector mode or emitter follower. This works as we said in theoretical class, it works as an isolation stage. Now let's see the both plot and its frequency characteristics. The frequency characteristics, I run it for a little bit more because for both plot, you should measure it for a few seconds. Reverse it. I increase the scale a little bit so that it is easy to see, right? So mid frequency, mid band gain is minus 0.07 dB. Negative gain. That means you know that common emitter, this particular emitter follower, its output voltage is little less than the input voltage. It is minus 0.07. So what is the 3 dB points? So this say 0. Let us consider 0. So we should see minus 3 and minus 3, right? We shall find out minus 3 is minus 33, minus 3.3. This is minus 2.966. So minus 3. And the frequency is 156.418, say 156 hertz. So lower cutoff frequency is 156 hertz. Upper cutoff frequency also we shall go to minus 3 dB, minus 3 dB, sorry. This is minus 3.09. So let us consider this. The frequency is 26.4 gigahertz. So let us say this is 26 gigahertz. Now, if you compare This one, upper cutoff is 26 gigahertz. Common base upper cutoff is 66 megahertz. That means for common emitter, upper cutoff is very, very high. That means this transistor works for this amplifier will give you the result for very, very high frequencies also. So this is how you test and measure common collector and common base modes, right? Lastly, I shall show you because in your syllabus I found there is a multi-stage amplifier model also being talked about. This is a multi-stage amplifier. RC coupled. This is the same amplifier is repeated here. Same amplifier is repeated here. Only these coupling capacitors are little different. Because the coupling will depend upon I showed you how to decide the value of coupling capacitors in theoretical classes a few lessons back. Here, audio equipment that you purchase, the amplification that you need, normally it's difficult to get that amplification in one stage. So there are multi-stage amplifiers. And of course, by simple arithmetic, the total gain is the product of the two gains. Right? So here, once again, let us see the oscillogram first. This blue line is the input. This blue line is the input whose scale is blue line is the input whose scale is 2 millivolt per division. So it is very, very small. It is 0 to 2 is maybe 0.6 millivolt or 0.7 millivolt, right? And this pink line, this red line, let me see this diagram. This is the red line. This red line is the output of the first stage. This is the red line, the B channel. It is 50 millivolt per division, 50 millivolt per division. So the 0 to peak value is something around 40 millivolt. And the pink line is the total output. Pink line is the total output and it is 2 volt per division. So it is about 1.7 volt peak. So this is how it is amplified from one stage to the other stage. To see actual what is operating, we put a voltmeter here. We put another voltmeter at the output of the first stage, another voltmeter at the output here. Right? Now we run it. We shall see the voltmeter reading. Output of the first stage here is 80. Let me zoom in a little bit, but this doesn't get zoomed. 86.3. This is 86.3 millivolt peak to peak. This is 1.13 millivolt peak to peak. So what is the first stage gain? 86.3 divided by 1.13. First stage gain is around 76. So I have read first stage gain in the 76. And what is the second stage gain? It is 7.44 volt divided by 86.3 millivolt. So gain is 7440 divided by 86.3. 86.3. This gain is around 86. Around 86. If you multiply 86 and 76, because we have taken approximate figure, 76 multiplied by 86 makes it 6,536. 6,536. And actual measurement is 7.44 volt, that is 7440 millivolt divided by 1.13 millivolt here, 1.13 millivolt here. This is equal to 6584. Slightly different because while putting these values 76 and 86, we made approximate figures. Again, and similarly, you could measure the input impedance, output impedance that we have already seen. Now, let us see the output plot. We shall run it again for a few seconds and see the board plot. Here, the mid-band gain is 76 dB. So 78.6. So minus 3 dB will be 78.6 minus 3. It is 75.6, right? 75.6. 75.6 is, yeah, 75.6. It is 232 hertz. So I have written here a 224. Let me write it 232. 232 hertz. And upper end gain is, this was 78.6. I have to make it 75.6. 75.6 is 980 kilohertz. So written 1 megahertz, so I rate it 980 kilohertz, right? Okay, this is the board plot. And let me see the board plot of common base amplifier. See, it is so widespread, right? Common collector amplifier also, board plot is quite widespread, up to 26 gigahertz. Common base is up to 66 megahertz. But stage amplifier, it is only, we have found it at only 1 megahertz. That means the flat band, we call it flat band, that a frequency band in which the gain is what we measure. We have measured a gain of 6536, and this gain is in a narrower band than a single stage amplifier. I do not know whether you have learnt it in your circuit theory subject. In electronics and communication, particularly in communication, there is a term called gain bandwidth product. It is a property of these electronic circuits or any four-terminal two-port network, that if you increase the gain, the bandwidth will lower, so that the product of gain and bandwidth remains more or less same. This is a particular inherent property of these two-port networks. You by multi-staging amplifiers, what do you get? You get more amplification. But mind it, you get less bandwidth. But of course, if this is your audio amplifier, this is enough bandwidth. Bandwidth is up to 980 kilohertz. So audio signal is hardly up to 10 kilohertz. So you are good enough. But if you are using this amplifier for high frequency application or a wide band application, then this amplifier will be a failure. Maybe you need an amplifier whose gain is flat from 1 kilohertz to 1 gigahertz. You will need it. Then this application is a failure in that case, you have to go for a completely different design, which also maybe you will learn in your subject of designing high frequency amplifiers. So this is the internal and intrinsic properties of. I think we have come to the end of this module where we have discussed nitty-gritties of common base amplifiers, common emitter amplifiers, and common collector amplifiers. We have learned how to measure its input impedance, how to measure output impedance, how to measure current gain, how to measure voltage gain, how to measure its bandwidth, initial F1, F2, lower cutoff frequency, upper cutoff frequency, and what happens when you multi-stage the amplifier. If you multi-stage the amplifier, gain will be higher, but mandate your bandwidth will be lower. Right? So today's lesson we finishes here, and in our next lesson we shall go to a different module, and we shall discuss power amplifiers and feedback amplifiers and a little bit about high frequency characteristics of BJTs and BJT amplifiers. Right? So this module, we finish it here today. Thank you.